Hello everyone, today we're looking at 19.4, energy levels in atoms, and what we'll look at is this thing called energy levels but of electrons in isolated gas atoms. We'll refer to the idea that energy levels have negative values. We'll look at emission spectral lines from hot gases in terms of transition of electrons between discrete energy levels and emission of photons. And then we'll look at an equation HF equals delta E, or HC over lambda equals delta E. So, top right, as ever, you've got your specification comments that we need to be referring to. But before we do that, let's just go through this first slide. So when electrons are bound to atoms in a gas, they can only exist in one of a discrete set of energies, so energy levels of an electron. So at GCSE, you'll be familiar with the idea that in the middle we've got the nucleus, and in the first shell there might be 2 electrons, and then in the next shell we might say 8, etc. But you've got the idea that electrons have to be in a certain position and they can't be anywhere else. So the electrons, we would say, are bound to the atoms and they can only exist in a certain place. That's a certain energy level. We also would say energy levels are negative. So if we wanted to move one of the electrons, let's say this one, if we wanted to move this electron away, we would have to put energy in. So energy levels are negative as you need to put energy in. Energy is required to remove an electron from the atom. So energy would go in and the electron then would be able to move out. So for example, if this was, say, minus 20 joules, in order to move the electron from here to here, so it's got no joules, we would have to give it 20 joules of energy. So as the next bullet point says, when an electron has 0 energy, so 0 joules, it has escaped from the atom. So that's when we might call something ionised, if something's gained or lost an electron. So in this case, it's lost an electron. The electron has now got 0 joules of energy. It's escaped. And the energy level with the most negative value is the ground state. So that we're talking about the electrons closest to the nucleus at that point. At GCSE, you would have heard of things like electron shielding. The electrons in the centre, the ones closest to the middle, they're the ones that are like most closely bound to the nucleus. So if we wanted to remove an electron, it would be far easier to remove the electrons around the outside compared to the ones in the middle. So that's why it says here, the ones just here are the most negative. They're the most difficult to remove to become free. We also refer to something called an excited state. So when an electron moves from a lower to a higher energy level with an atom in a gas, we call that the excited state, and it requires external energy. So what I mean by that is sometimes you might want to move an electron, or an electron might move itself, to another energy shell. So we're assuming that this electron here has left, but sometimes another electron might get a smaller amount of energy and just move to a less negative value. So this value just here might be at minus 10 joules. So the electron might jump from here to here. So it's still bound to the atom, but just slightly more loosely bound. But either way, you need to still give it that external energy to move it from one shell up to the next. This is another example of the same as the one I've just drawn just there, except rather than circles, they're horizontal lines. And this is similar to the diagram in figure 2 on chapter 19.4 in your book. So the lowest energy level down here, the ground state, that would be the equivalent of the electrons closest to the atom. And then the next circle would be classed as n equals 2. So that would be this one. N equals 3. And then that would be this one round here. And so on. And as you can see, these energy levels do exist, but there might not be any electrons sitting on them at that moment in time. So if we do have an electron on the ground level and we want to move it from the first shell to the next shell, we have to give it energy. It starts off, in this case, with minus 13.6 electron volts, and the next energy level has minus 3.39 electron volts. So the difference between the two numbers, if you put it into a calculator or perhaps do it in your head, is 10.21. So we spoke earlier about the word discrete. You've got to give the electron exactly 10.21 electron volts to move from n equals 1 to n equals 2. The electron can't accept any other value, so it can't accept 5 and it can't accept 11 because it goes too far above. So when we talk about the physics here, you've got to have discrete energy levels. The numbers have got to be exact, jump from one place to the next. If you gave it exactly 13.6 electron volts, the electron would then get to 0 electron volts, and as I mentioned earlier, that's when you get ionisation. So there's quite a lot of information on this page, but if we can just to start look at still this area just here. So it's the same diagram as the one before, apart from we've got an arrow going up and we've got an arrow going down. So let's focus on this arrow going up first. So this one now, this electron has been given exactly 12.09 electron volts. And if you add that to minus 13.6, that takes you to minus 1.51. So the electron would be sat here. But just like when you throw a ball up in the air, it comes down again, the electron does the same. And eventually, not always immediately, but at some time later, the electron falls back down to the ground, just like that ball would if you threw it up into the air. But the difference is the ball, as it falls down, doesn't behave exactly as an electron does. When an electron goes back down here and loses the energy it's been given, what you see is a photon being made. A photon is emitted. So the electron gets excited, and as it becomes de-excited, a photon is emitted. And because of the conservation of energy, it's the photon that gets emitted of 12.09 electron volts, the one that we started with. Now there's an equation, E equals HF, or written differently, HC over lambda, because F equals C over lambda. So E is our change, or delta E is our change in energy, H is Planck's constant, F is our frequency, C, speed of light, and lambda is our wavelength. In that figure 2 example, you've got the electron making a transition, as it says, and sometimes the electron might go down all the way, or it might go in 2 stages. So occasionally you might excite the electron, some electrons might go straight down, and some electrons might jump and release 2 photons. But either way, the total energy released is equal to the energy that it went up by. So if we just look at the worked example emitting photons. So they use the information in figure 2 to determine the frequency of the 2 photons emitted. So the first step is to calculate the change in energy in joules for each electron as it drops from the higher energy level to the lower one. So if we focus on the first photon, it starts at minus 6.8 and it ends at 6.8, sorry, and it starts at 1.5. So the difference is 5.3 electron volts. To convert electron volts into joules, as a reminder, you multiply by 1.6 times 10 to the minus 19, which of course is the charge of 1 electron. The second photon goes from minus 1.5 down to minus 3. So the change in energy is 1.5 electron volts, and again to turn electron volts into joules, you multiply by 1.6 times 10 to the minus 19. So the energy in joules, 2.4 times 10 to the minus 19. So we're still trying to find the frequency. We want to determine the frequency. We've found the energy, so we can use our equation E equals HF, or rearrange for frequency equals delta E over H. So for the first photon, our change in energy is that 8.5 times 10 to the minus 19. We can divide that through by Planck's constant. So for the first photon, that works out at a frequency released of 1.3 times 10 to the 15 hertz. And likewise, the second one gives us 3.6 times 10 to the 14 hertz. Now you'll note that the first photon has a higher frequency, and that's because the energy levels are greater. They're directly proportional to each other. So the bigger the energy change, the bigger the frequency of the light that gets emitted. Okay, so if we just go back to where we started at the beginning of the lesson, and let's just think about maybe a lesson in chemistry that you've had, probably at GCSE, where you put a metal into a Bunsen burner flame and it gave off a colour. Well, that's exactly what's happening here. It's a flame test. So if you've got a bit of metal, you put it in the Bunsen burner, it absorbs the energy. So what happened was the electrons absorbed energy, they moved to a new energy state, and then as they cooled down, or as they then moved down, they released a photon of light. So it gave off a wavelength, a colour that we could see with our eyes. And that was what's happening. So when we look at stars, and this is for next lesson, this is very useful because in a laboratory we can burn an element, if you like. We can see the colour that gets released. And then we can look at stars, we can see what colour the stars are. So then we know what element it is that's in the stars, and then we can start working out things about temperature and the type of fusion reactions that are happening, also based on its luminosity and of course its size. So for homework, please have a go at the summary questions of 19.4, and again they should be on Caboodle for you, or they're also just there, so press pause on the video and you can see them. Next lesson we'll be looking at hydrogen and the pattern that hydrogen gives off in particular in more detail. So you might also want to look at this using the internet. We don't need to know about the Lyman-Baumer or Paschen series, but it's something that you can look at. So they're just the lines that were named after the people that found them or discovered them. So each of the arrows corresponds to a different transition. So I mentioned earlier that you don't have to jump all the way down from one to the bottom straight away. You can take your time if you like. You can take one step rather than 3 or 4 at the same time. So that, and each one's called a transition. So as it moves from a higher to a lower transition, that's the one that produces the colours or the frequencies of light or the wavelengths. And then each of those arrows corresponds to the patterns that you can see here, and they're called line spectra. And we'll look at those again next lesson under 19.5 spectra. So that's it for today. Have a go at the summary questions then please, and carry on making additions to your notes. Any queries or questions, please do get in contact, as I'm very happy to help, and I hope you're all doing okay. See you soon. Bye bye.